Hey everybody, this is Mike Bartles from the Hydrologic Engineering Center. This lecture is part one within a series of lectures devoted to parametric modeling from a hydrology and hydraulics perspective. Within this video, I'm going to introduce the subject and set the stage for future discussions. This lecture will not be an exhaustive, detailed look at all the various aspects of parametric modeling. We won't be deriving equations or getting deep into math. Instead, we'll view the topic from a 30,000-foot perspective and focus more on concepts and big picture items. The next few lectures will delve into more detail. First, let's discuss what we mean when we talk about a model in a hydrologic or hydraulic modeling context. So a model is a formal representation of a theory. Take, for instance, infiltration into soil. Infiltration in the real world is complicated, as shown in the image to the right. Water with blue dye was placed on top of this soil and allowed to infiltrate over a few hours. After a while, a backhoe dug this hole and allowed for us to see how far individual strands of dye had progressed downward. A specific representation of infiltration would be the green and amp method, which simplifies the process but still preserves important aspects. Modeling allows engineers to estimate the behavior of a system that is not otherwise captured in time and/or space. Questions that could be answered with a model include: what will the river flow be 3 days from now? How much runoff will be generated given 20 inches of precipitation over 3 days? How will the water surface elevation change if a levee were to be constructed? Or what is the likelihood of stream flow exceeding 20,000 CFS? Analytical models, like the aforementioned green and amp method, usually include general principles and a set of statements. This allows for analytical models to be extrapolated beyond what has been observed, which is of particular interest to us in this profession, given that we're oftentimes interested in extreme events that haven't been observed, like, say, the 1 in 100 annual chance exceedance for floodplain studies, or the probable maximum flood for dam safety studies. Conversely, empirical models usually omit any principles and simply use the data. So this is analogous to interpolating between known points. However, this leaves us high and dry when we want to extrapolate, because you can extrapolate with empirical models, or at least it's not easy or straightforward. Parametric modeling and analytical frequency analysis are equivalent, and the two phrases can be used interchangeably. The result of this type of an analysis is a fully parameterized probability distribution and median values. Additional steps can be taken to estimate confidence limits and mean estimates. For something to be parametric, the parameters must be located in finite dimensional space, so they cannot be imaginary. An example of an analytical model is shown on the right, which visualizes the cumulative distribution function of a fully parameterized log normal distribution. The two parameters of this distribution are a mean and a standard deviation. The median values are signified by the red line. Observed data is shown with the blue bars. A model, in the sense that we're interested in within this set of lectures, consists of both an analytical distribution and a fitting method. The same analytical distribution can be parameterized using two different fitting methods to produce a different parameterization. This is shown on the right. The green and red lines represent the same analytical distribution, say, for example, generalized extreme values, but they have different parameterizations because they were fit to the blue observed data using different fitting methods. Now, I'll describe some of the more commonly used analytical distributions and fitting methods in a future lecture. The complement of parametric modeling is fitting in an empirical distribution using graphical techniques. That would be the equivalent of drawing a line of best fit through the blue observed data in the image to the right. However, like I said before, you can't easily extrapolate beyond the range of the observations. Parametric modeling is performed all the time by tons of hydraulic engineers and modelers all across the world. So two examples of commonly asked questions that can be answered using parametric modeling are: what is the probability that a quantile will exceed some value? And given some probability, what is the corresponding quantile? This image is an instance of the first question. What is the probability that a quantile will exceed some value? So start on the y-axis at some important value, for example, 4 inches of precipitation. Then trace a horizontal line until you intersect the model. Then trace a vertical line down to estimate a corresponding probability. In this case, there is an approximate 1 in 50 annual chance of exceeding 4 inches of precipitation. This image is an instance of the second question. Given some probability, what is the corresponding quantile? This time, start on the x-axis at some important probability, for instance, the 1 in 500 exceedance probability. Then trace a vertical line upwards until you intersect the model. Then trace a horizontal line to estimate a corresponding quantile. In this case, the 1 in 500 annual exceedance probability precipitation is approximately 6.75 inches. Parametric modeling has many advantages when compared to graphically fitting an empirical distribution. The biggest advantage is that a fully parameterized analytical distribution allows the user to estimate quantiles throughout the entire range of probability from 1 to 0. Also, parameters can be pooled and regionalized to improve estimates everywhere. Confidence limits can be computed, and the calculations that are used to fit an analytical distribution are tractable and repeatable by other engineers. And this isn't necessarily the case when graphically fitting an empirical distribution. This becomes incredibly important when comparing, say, 1 in 100 annual exceedance probability floodplains in the eastern United States against those developed on the West Coast. Now, they better mean the same thing in order to prioritize funding for infrastructure or watershed management. However, there are some disadvantages to parametric modeling when compared to graphically fitting an empirical distribution. Now, first and foremost, a model must be assumed up front. We'll discuss the implications of this assumption in greater detail later. Some data will not be well fit using commonly employed models. Now, this includes regulated data or stages, which are shown to the right. So notice the sharp discontinuities and multiple changes in slope throughout the full range of probabilities. And it's going to be really hard to fit a meaningful analytical distribution to this data. A false sense of accuracy can also be inadvertently implied when using parametric modeling. This is analogous to reporting precision to a result to the millionth decimal place. Finally, computations can take more time than when using graphical techniques. Lastly, I'd like to introduce the steps that are used when performing a parametric modeling exercise or fitting an analytical distribution, and we'll revisit each one of these steps in the next few videos. First, you must develop a representative dataset. Second, you must select a probability distribution and fitting method, which constitutes a model. Third, you have to fit the selected distribution to the data in order to compute the parameters of the distribution. Fourth, you must verify the appropriateness of the model given the sample. And finally, you can then use the model to predict variables or quantiles of interest. So each one of these points, like I said before, we're going to discuss in greater detail within the next few lectures. In this video, I introduced parametric modeling along with some of the theory, advantages, and disadvantages when using this method. We'll delve further into the parametric modeling steps I briefly introduced at the end within the next few videos. Thanks for watching. I'll see you in the next one.